Welcome to KotlinBytes. My name is Jacob, and in today's video, we'll be discussing callbacks and closures. Callbacks and closures are oftentimes used for similar purposes. The main purpose is often asynchronous programming or event listening. Our example today shows not only the benefit of using a callback or closure in your code, but also expresses how Kotlin has implemented a clean and simple closure syntax that should be used often where it makes sense. Let's first explore our example without the use of callbacks or closures. Our example shows two baristas, Fred and Sam. Each of them have their own coffee maker, and each can accept a coffee order. As you can see, when accepting an order, each barista will ask for the type of coffee requested. Knowing the coffee type, the barista will use their coffee maker to brew the coffee requested. Once the coffee is brewed, the barista will announce that the coffee finished brewing and is ready. The coffee maker can only perform one task, that is, to brew coffee of a given type. In this example, brewing coffee is simulated by delaying execution of the system thread. I'm using a helper function that I've created to suspend or delay execution of the current thread. The implementation of this delay function is not important to today's topic. Just know that it represents the coffee maker in a busy state and will only return the coffee once complete. The coffee type defines the brew time for each type of coffee. As shown here, I've listed a few types of coffee that one might order, and I've assigned each arbitrary brew times. To test our scenario, we'll have Fred and Sam both accept orders at nearly the same time. Fred will first accept a latte order, which will take 875 milliseconds to brew. And Sam will immediately after accept an Americano order, which should take only 300 milliseconds. If we run this code, we'll notice that Fred finishes first, even though his latte took over twice as long to brew. When we reverse the order of accepted orders, our result is flipped. This is an example of a bug caused by synchronous or blocking code. The fix would be to use asynchronous programming. The use of a callback is a solution to this issue. A callback is defined as any executable code that can be passed as an argument to other code. The other code is then expected to call back or execute the argument at some given time. Setting up a callback is fairly simple. We need to create an interface that represents the code to be executed at a delayed time. Our interface will only contain one function, onCoffeeBrewed. This function will accept an argument for the prepared coffee. Our brewCoffee function will now need to accept another argument for this interface callback. Since we are using a callback to give us a result at a later time, we can remove the return type to this function. This indicates that the caller of this function should not expect a result immediately, but rather at a later time. Inside of the function, we simply call the onCoffeeBrewed function upon the callback reference once the coffee is ready. Now, back at the barista. Before, the barista was waiting at the coffee machine for the coffee to finish. This callback allows for the barista to start the coffee machine, then accept other orders if requested. Once the coffee machine is finished, they will be notified that the coffee is ready to be given to the customer. For this to work, we must add our callback listener to the brewCoffee function. We will say that the barista should be notified by using the this keyword. For this to work, we need to declare the barista as a coffee brewed listener. Finally, we'll be forced to implement the onCoffeeBrewed function. I'll move the print code to this function as well. I love how oftentimes object-oriented programming makes logical sense in the real world. This is an example of that. The barista is not only taking orders, but is also aware when their coffee machines are finished making coffee. Of course, I'm aware of how real baristas make coffee. Not all coffee requires just a simple press of a button like a Keurig. However, for the sake of simplicity, let's assume that this is the case. Alrighty, now that we've implemented our callback, let's try executing our code again. You'll notice that nothing has changed. This is because, although we are using callbacks, our code is not yet asynchronous. Our callbacks are being executed in the same way our results were being returned in the past. Our culprit for this bug is the way we implemented our delay. our delay is currently blocking one thread. The fix is to use an asynchronous delay, such as this one. I will pull the callback into this asynchronous delay to fix the problem. Before, to follow our analogy, when the barista pressed the coffee maker start button, the coffee maker would run, however the barista would be stuck babysitting the coffee machine until the coffee was ready. Once ready, the barista and the other baristas would be free to accept more orders, but only once the first coffee was finished. Adding the asynchronous delay is like saying that the coffee machine is able to brew coffee without any barista supervision. Once we run this code, we'll see that the Americano finishes first, which is the expected result. Callbacks are also able to be inlined and made anonymous like this. Using an anonymous callback can be useful if your class doesn't conform nicely to the interface, or if the operation is far too simple for the interface implementation overhead. As you can see, the result is the same. However, if you take this anonymous approach, there is a better way, and that's closures. Callbacks are a common technique in many languages, including Java and Kotlin. If a callback interface only has one function, a callback can typically be converted into a closure. Or more generally, a lambda. A lambda is a function that can be stored as a variable. These are also referred to as first-class functions. A closure is a way of using a lambda, similar to that of a callback. Coming back to our coffee maker, we can replace our listener interface with a lambda parameter definition. To define a lambda parameter, we first use parentheses to define the parameters our lambda will accept, and then the arrow and finally the lambda return type. In our case, the brewed coffee will be the accepted parameter, and unit, which is similar to void or nothing, is returned, just like our previous onCoffeeBrewed function defined in our listener interface. Once the coffee maker has finished brewing the coffee, it simply needs to call that onBrewed lambda function with the made coffee. Back to the barista. We will replace the anonymous callback with the lambda declaration syntax, denoted by the curly brackets. We can define the coffee argument like so. However, since there's only one argument, we can remove explicitly writing it and use the implicit it argument instead. In certain cases, it makes sense to add the explicit argument name, but for now, we'll leave it off. Running the code, we'll notice that it works the same as before. Since the lambda is the last parameter in our brew coffee function, Kotlin allows us to move the lambda outside of the parentheses, and again, the code runs the same. In this scenario, we are using the lambda as a closure. Finally, to drive home this point that lambdas can be stored as variables, let's move our onFinished closure lambda to a field variable. In its current state, we'll need to define the arguments or parameters. However, you can also define the lambda as a type on the property if you would like to still use the implicit it argument. And of course, this also works as expected. That's it for today. If you guys learned something, consider a thumbs up. If anything was unclear or if you have additional questions, please comment below. I would love to start a conversation. Otherwise, have a great day.